My name is Katherine Hollingsworth. I am the webinar moderator. It's a pleasure to return to another webinar with you all today. And today I would like to welcome Gerhard Engel and Erich Wimmer. Dr. Gerhard Engel leads strategy and innovation here at Materials Design, leveraging decades of expertise building and commercializing software solutions for science-based industries. Gerhard holds a PhD in physics from the University of Cambridge and has published more than 30 scientific papers in the area of computational physics and atomistic simulations. And Dr. Erich Wimmer is our co-founder, chief scientific officer, and chairman of the board here at Materials Design. Erich led the development of a multi-million-dollar per annum business in the chemical and pharmaceutical market for clay research in the 80s and 90s, and he organized industrial consortia, developed the Unichem simulation environment, and now leads a consulting team that creates industrial value for clients using computational materials science and engineering methodologies. In addition to his hands-on practical industrial experience, Dr. Wimmer is author and co-author of over 130 scientific publications and several patents, and has given numerous lectures worldwide. So we are very much looking forward to their presentation today. Without further ado, let me pass the microphone over to you, Gerhard. Welcome and thank you for joining us here today.
Thank you, Kathy, for the introduction. Today's webinar is on a very exciting topic, which is the topic of nuclear fusion and what we can do in materials modeling to contribute to this very active area of research. The webinar is roughly divided into two sections. In the first section, I'd like to introduce the opportunity and the technology for fusion if you're a material scientist and a modeler, and how you can contribute basically to this effort. What are the key challenges? What are especially the materials needs that have arisen within this very nascent but rapidly growing industry? And then Dr. Wimmer is going to talk about computational materials engineering insights and predictions, basically by providing a number of very interesting examples about how materials modeling can contribute to research on materials that are suitable for commercial fusion applications. And he'll conclude by talking a bit about a materials design fusion initiative called Materials Design Fusion Alliance. So you're all familiar. I won't go into too much detail really on what nuclear fusion is. It offers the promise of unlimited energy, but it's not so easy. So basically, in the standard fusion approaches used today for most fusion applications, you have a deuterium and a tritium atom fusing and releasing a lot of energy, mostly kinetic energy of a neutron, and also basically they're fused into a helium atom. And the energy released corresponds to the mass difference between the reactants and the products in this nuclear reaction. In principle, you can have fusion reactions for many of the lighter nuclei in the periodic table, up to about nickel. In theory, if you combine nuclei, you can gain energy released from the nuclear force. Now, the challenge, as I'm sure you're all aware, is really that the atomic nuclei, like in this case, the hydrogen nuclei, repel each other very strongly through the Coulomb barrier. And so in order to get those nuclei to fuse, or to at least have a reasonable chance of quantum tunneling through this barrier, you need very high temperature, very high pressure, and long confinement times. And so most of the effort, if not all of the effort over the last 70 or 80 years to try and develop commercial fusion opportunities has really been in achieving the conditions that are suitable to make this nuclear reaction happen. I'll start out by talking a little about investment in fusion energy and why it makes sense. So obviously fusion energy is really one of many avenues that mankind is pursuing to meet the increasing demand for carbon-free energy, which likely outstrips the growth of traditional renewable energies, and even in combination with traditional energy sources. there is definitely scope for a cheap and abundant energy source that's going to drive our increasing demand for energy. And so the chart on the left just shows a few data points on that. In 2024, the global electricity consumption increased roughly at a 4.3% annual rate. And as you can see, much of the demand is coming from obviously industry, but also electric vehicles and air conditioning, which are all growing rapidly. Data centers, AI, and all that, of course, also contributes to the demand. Now, the advantages of fusion energy are, of course, no greenhouse gas emissions compared to solar and wind. It also offers 24/7 availability. In principle, the supply of fuel is unlimited. You have a very high energy density. It's inherently safe. Minimal long-lived radioactive waste. There is some, as we'll see, from the nuclear reactions that are taking place. Compared to fission, nuclear fission, there's no risk of nuclear proliferation. And potentially, although that remains to be proven, it could be compact and scalable. The challenges are really the technical complexity of fusion reactors, and therefore the field requires pretty large upfront investments. Tritium is one of the more easy to fuse fuels. There is, at least in the initial phases, a supply issue, although there are ways of breeding tritium as part of the process. And from a materials perspective, the key challenges are mostly around the fact that you need materials that withstand extremely high temperatures, and that can also withstand the neutron damage on the materials that are happening. And there's also a number of other bottlenecks, of course, that are all contributing to the cost. And so for commercial applications of fusion, it's ultimately the key goal of all of us as a community to bring down the cost of this extremely promising energy. So concurrent with the promise of fusion, there's really over the past years in particular been a very strong increase in investment. And I'll talk both about public and private investment. In terms of public investment, the biggest project worldwide that's currently going on is probably ITER, which is a facility being built in the south of France, and was started in 2006 as an international consortium between the US, China, European Union, India, Japan, Korea, and Russia. And so far, the investment, depending on what you count and don't count, is definitely above $20 billion. Some people put the figure much higher than that. But also individual countries, of course, are heavily investing. The UK Atomic Energy Authority, for example, with its STEP and Liberty programs, are investing just in 2025, £410 million. Europe, through the Eurofusion Consortium of National Fusion Research Institutes, is investing heavily. Japan has several fusion reactors and fusion projects ongoing through the Moonshot program. South Korea had a major milestone last year, for example, where they actually achieved a maintained plasma at 100 million degrees centigrade for about 48 seconds. And they've really publicly acknowledged public funding in the range of almost $1 billion. China's total investment isn't very well known, but again, many initiatives are happening there. And of course, last but not least, the United States has a pretty high public budget and also heavily invests in public-private partnerships and contributes through all of that to things like the D3D facility in San Diego, also contributes to ITER, and as I said, many partnerships. On the right, just very briefly, if you look at the DOE budget in a bit more detail, it's split into 5 main funding groups, and at least 2 of those, theory and simulation and fusion materials, impact directly on opportunities for material scientists to contribute to this really important field. In terms of private investment, that's really what's triggering a lot of the excitement, especially in the US, but also very much in Europe, Japan, even as far as New Zealand. More and more private fusion companies are being started. And that really speaks to the massive progress that's been made, certainly over the last decade, in exploring alternatives, but also just really solving many of the technical problems related to confining the plasma and really making this work in a commercial setting. So there are worldwide about 50 at least private fusion machine companies and many more technology providers. Well over 100 research organizations are contributing, and take some data from the Fusion Industry Association and Fusion Energy Base that's publicly available. The chart on the bottom left shows where the companies are located. The chart on the bottom right shows the level of investment. There was a spike in 2021 related to a large investment of almost $2 billion for Commonwealth fusion systems. But in general, you see investment in the US is ramping up, and investment in China is ramping up even faster. And of course, other countries are equally contributing. This chart just shows again that really the investment in private fusion companies to turn this into a viable and really interesting industry started around 2018 and has really every year new companies are joining the fray. Really it demonstrates that there's a lot of excitement and progress in this field. So I'll move on to talk a little about the technological aspects. Again, apologies to those of you who this is very familiar to, of course, but I know we have a broad range of people in the audience. So commercially, the most commonly used reaction is that of deuterium and tritium, mainly because it requires the relatively lowest temperatures and pressures to make it happen. In that case, most of the energy of the reaction is released in the form of a very high energy neutron, which basically needs to be slowed down in order to extract that energy. And you can, for example, use lithium blankets and the like to achieve that, and basically disperse the energy in a way that can then be used to produce heat in the form of steam, for example, or other ways. Many experimental fusion reactors also experiment with the deuterium-deuterium reaction, even though it's more difficult to achieve. Deuterium is much more abundant and easier to get, so many of the tests can be carried out with that. In that case, also a lower energy neutron is generated, and in fact, tritium is also created by 50% of that reaction. Because of the challenges on the right-hand side that deuterium tritium fusion poses, there's also been a number of attempts to achieve aneutronic fusion, basically a type of fusion where no neutrons are released and instead the energy is released in the form of alpha particles, for example, as in the PB11 fusion, which actually one of the earliest companies, TAE Fusion, started to explore. That I think they got founded around 2008 or thereabouts, and really have made a lot of progress since then. One advantage of generating an alpha particle is that in principle it's electrically charged, so you can conceive direct energy conversion rather than needing to slow it down through some materials process. Both of these PB11 and deuterium helium-3 fusions happen at much higher temperatures and confinement, so that's one of the downsides of the methodology. So looking now how this is being realized in reality, the most common fusion technology, or the most common way to achieve fusion reactions in a plasma with the requisite density, temperature, and also retainment time is magnetic confinement. So this is by far the most researched methodology. Typically what people use is a tokamak, or more recently experiments with the so-called stellarator. And so I won't go into too much detail here, but the field lines of the magnetic fields are constructed very carefully to allow the plasma to be as stable as possible, circulating within this tokamak and being able to heat that plasma and effectively facilitate fusion reactions. And the stellarator achieves those kind of same plasma confinement goals through a more complex technological design with a twisted magnetic field, but at the same time that has advantages for plasma stability. The challenges are plasma instabilities, the need for tritium in most of these configurations. It needs to be bred and handled. And more on the material side, the fact that this plasma doesn't entirely stay away from the walls of the tokamak, so you need materials that are able to withstand extreme neutron bombardment, but also temperatures, and this leads to neutron damage. The magnets themselves are a challenge themselves, and there are materials challenges within the magnets. And of course, ultimately, there's some waste from the neutron irradiated materials that needs to be handled. There's also a levitating dipole design at the bottom, which is quite fascinating. You can read up. The company in New Zealand have proposed that based on earlier theoretical research. The second class of technologies is called inertial confinement. This is closer to the concept employed in the original hydrogen bomb or thermonuclear devices, except you try to achieve the high densities by directing lasers or mechanical pressures or implosions onto a target which contains a fuel mixture. This is realized, for example, in the Z machine at Sandia National Lab, and by a number of companies that are working on this approach to fusion. Just as a small aside, not currently commercially explored, but there's also something called muon catalyzed fusion, which actually happens at room temperature, where you replace the electrons in the hydrogen molecule with a muon, which is about 200 times heavier, and that brings the nuclei much closer together to such a degree that actually fusion happens naturally, even at room temperature. However, the energy going into the creation of the muon and other technical problems prevent this from being a commercially viable mechanism to date. So going into a bit more detail on the materials challenges, I already talked about neutron radiation. So actually, let me start on the right. So this is a cross-section of a typical tokamak. You have the first wall as the plasma facing material. Quite important at the bottom is something called the diverter, which is where the gases that ultimately come out of the fusion reaction are extracted, and that needs to withstand particularly high radiation and also temperatures and heat flux. Beyond the first wall, you have a lithium breeder blanket. You have a shield, typically the vacuum vessel surrounding all of this, and the magnets mostly sitting outside of this construction. And so all of these materials are basically subjected to radiation. They're subjected to stresses, corrosion, mechanical loads. So in the case of the blanket, the corrosion comes basically from the interaction with materials that carry away the heat. The helium generation causes, again, other defects in the diverter or even transmutations that aren't listed here, and so on and so forth. So really what's needed is very high performance materials that can withstand the extreme conditions inside a tokamak. And basically in the following, I'm going to focus mainly on the magnetic confinement tokamak type technologies. Okay. A little more on neutron damage. I won't go, in the interest of time, into too much detail on the right-hand side, except to say that, again, defects, their creation can happen on the level of nanoseconds, but also many phenomena really from a modeling perspective require modeling across the length scales. Some of them will happen over periods of seconds, minutes, hours, or even years in the case of long-range diffusion, segregation, and so on, and irradiation-induced microstructural changes. And using current designs of fusion technologies, there are estimates that some of the components of a fusion reactor may need to be replaced every few years. Obviously, one of the key goals of materials research and making technical progress is to increase those maintenance times so that commercially the costs go down. But breeder blankets, diverter, and so on, it's very possible that those won't withstand or won't live forever, for decades, but have to be replaced more quickly. So the main materials used to achieve this are a lot of metals and alloys. Tungsten is very prominent, for example. A lot of research is going into various alloys, multi-component alloys. Often the way the components are being made is through additive manufacturing, so powder metallurgy is important. Steel plays, of course, a huge role. So again, a lot of research going into that. Second class of materials is ceramics and coatings, things like silicon carbide, titanium carbide, tungsten carbide, and special coatings to, again, protect the substrate from the ferocious conditions inside the tokamak. Ceramics are very important, especially for the breeders and amplifiers. And sort of a separate topic, but equally important, is building strong magnets and insulators, for example, superconducting magnetic materials. And in the case of, well, all of these technologies, but also inertial confinement, lasers play a key role typically to really heat the plasma appropriately. Yeah, sorry, I forgot, on the right-hand side there were pictures of helium bubbles and some high entropy alloy powder. So the helium bubbles really shows you the significant damage being done by a lot of processes inside the reactor. So I'll conclude my section here by just highlighting that in terms of materials modeling, there's really a large and growing number of publications that cover nuclear fusion and that are relevant for nuclear fusion. So in total, using Google Scholar, there's probably about 800 publications just using the leading density functional code WASP, which is available through materials design in conjunction with nuclear fusion. And other Google search results, if you search for WASP and alloy, for example, or WASP and tungsten, ceramics, high entropy alloys, oxide strengthened materials, all of this, you find thousands of publications that really have studied these materials using materials modeling approaches. Also, in some cases, like phase diagrams for alloys, methods like CalFERT are being used. And again, the parameters going into some of these calculations can often be deduced from first principles or basically materials modeling. And Dr. Wimmer is going to talk in much more detail about this. I picked 3 publications here. The first one is about alloys, very interesting work, recent work on alloys and designing those alloys in extreme irradiation environments. Another one is about the coupling effects of molten salts. And the third one is pretty close to what Dr. Wimmer is also going to talk about a bit. It's about really tungsten-based materials, alloys, and disguise, and how they behave under fusion power plant conditions. So with that, I will pass over to Dr. Wimmer, who is going to take us through some real examples of materials modeling for fusion applications.
Well, thank you very much, Gerhard, for this very instructive and fascinating overview of the technology, of the industrial activities, and the commitments that we see in terms of investment in this field. So I think the promise of unlimited energy is, well, coming closer to reality. So as you pointed out, key is really the choice, the design, and the understanding of materials. In a sense, we know how to produce the nuclear fusion of the sun. We just need a bottle to put it in. Here, I want to illustrate the capabilities of computational materials engineering with these examples. First, an example will be the irradiation of materials properties. Then the dynamics of hydrogen, deuterium, tritium, diffusion, release, and trapping in these materials. Then we'll look at the effect of transmutations, and that will lead us into the world of cluster expansion and phases and phase transformations. And we end up on the microstructure level how to predict the evolution of a microstructure. So let's start out with a simulation that was done by our colleague Gerrit Tow, namely taking a piece of tungsten and simulating a collision cascade. So let me launch this video here. So essentially what you do is you impart a very high momentum on one atom, that's the knock-on atom, and then you watch how the energy dissipates. Now I should say that in order to do these simulations, you need kind of increasing time scales and time steps, because you want to start out with very, very small time steps, and then as the system evolves, you can make larger and larger time steps. So what you basically have seen is that you get this initial kind of explosion of defects, but then because of the heat that you're generating locally, there's also healing going on, and you're ending up with a relatively few localized, what metallurgists would call crowdions of that. So if we now look close and ask the question, well, we have transformed the materials, we've included and induced the defects. How do these defects change the material's properties? And in order to do that, we have done the following simulations. We've created Frankel pairs of increasing concentration. A Frankel pair is essentially when you take one atom and you knock it out from its lattice side and eject it until it ends up somewhere in an interstitial position. So you're left with an interstitial atom and a hole. And you do this for increasing concentration, and then you take that initial structure and you anneal it and see what comes out. And well, not surprisingly, you're getting these type of crowdions. And as you increase the concentration of the Frankel pairs, what you see is a clustering of these defects. Here they're still isolated. Now they're clustering. So what does it mean for the material's properties? And we look at two key properties. One is the swelling, because from an engineering point of view, if your material under irradiation expands and swells, well, that induces stresses and could induce also materials failures. So what you see is that at the very beginning, when the defects are kind of isolated, you get the linear behavior, as you might expect. But very soon, you deviate very dramatically from the linearity, and you're entering in a regime that ends up with some sort of plateau, in the case of tungsten, close to about 1% of volume expansion. And that is due to the fact that at higher concentrations of defects, you get clustering of defects, and they kind of lead away from this simple linear behavior. So that's being produced and predicted by very accurate simulations. Now, just a word what's behind here. We're using a so-called machine-learned interatomic potential that was created by my colleague Michael Christensen. And that potential is trained on a large number, thousands of ab initio calculations. So you're getting the quality of ab initio, but the convenience of standard molecular dynamics force field simulations. So that's what you're seeing in the swelling of the volume. And if you look at the elastic moduli, Young's modulus, bulk modulus, shear modulus, as you might expect, at the very beginning, you get a linear behavior. Essentially, as you introduce these defects, in this case, under these scenarios, you get a weakening, softening of the material, and then plateauing of these elastic properties. So this is just for very specific conditions. In fact, the relaxation is done at room temperature, and at higher temperatures, the behavior may be quite different. So this is what you can do already with simulation. You get qualitative understanding of the structure of defects and quantitative data. How does a defect translate into changes in materials properties? Now, we have seen that in the plasma you have the deuterium and the tritium, which can be captured inside the tungsten. And so what we did here in this simulation, took a model of a small crack in tungsten, and inside the tungsten initially there is hydrogen. And now we are heating up that system, and very quickly you see that some of the hydrogen atoms escape from the surface. They are ejected, sometimes they return, sometimes they fly across the crack and re-enter the system. But overall, you see more and more hydrogen atoms diffusing from the bulk towards the surface, or this internal surface in this model. And amazingly enough, you don't create H2 molecules or the tritium or deuterium molecules, simply because the probability of a pair of H or deuterium or tritium atom has the ability to dissipate its energy and then bind is very small. Eventually, this will actually happen, but not in this particular scenario, which is kind of a surprise. Now, this is done using a very beautiful feature of VASP, namely machine learning on the fly. So you're starting out with an ab initio molecular dynamic simulation, and as you step forward, you automatically train a machine learned potential, and more you're using this machine learned potential to propagate the trajectory, and so eventually you end up with a custom-made machine learned potential. And in order to generate it, all you need to do is in the MedeA VASP interface, check one checkbox and says, well, use machine learned force fields. So that was done for this simulation. Now, in tungsten, radiation will create defects. We've seen this Frankel pair generation that leaves vacancies. And these vacancies are very strong traps for hydrogen, deuterium, tritium. So can we simulate that? And of course we can do that. We do have a very nice machine learned interatomic potential that allows us to simulate this scenario. So here the model is you take bulk tungsten and then you plug in this box 5 hydrogen atoms, and there's one vacancy, tungsten vacancy in the system. And as you can see, the hydrogen atoms diffuse very, very rapidly. Now the temperature here is 1,300 K, so it's very hot. And nevertheless, the hydrogen atoms get trapped inside the vacancy and stay trapped even at 1,300 K. So vacancies in tungsten are very strong traps. And analyzing this in more detail, you find that a single vacancy can trap up to 6 hydrogen, deuterium, or tritium atoms. Given the fact that they stay inside at such a high temperature means that if later on you want to recover the tritium, for example, from tungsten tiles, well, either you make sure that you anneal the vacancies so that the hydrogen has no way to get trapped, or you need to heat it up to very high temperatures. So again, simulations give you very detailed quantitative understanding and data of the behavior of hydrogen in tungsten. Now, I mentioned diffusion. How accurate can we actually calculate diffusion coefficients? Now, this is an early work done together with the Naval Nuclear Laboratory in the United States, where we looked at diffusion of hydrogen, deuterium, tritium in nickel. And here there's some very good and large quantities of experimental data that compare with. Bottom line here is you look at the open circles, those are experimental data points, and the solid lines are the computed results from first principles, using an approach that involves following calculations for getting the rates of the jumps from octahedral sites over tetrahedral sites into the next octahedral sites. Also, what this simulation clearly demonstrates is subtle effects due to the isotope changes, so hydrogen, deuterium, tritium. Those subtle effects are being properly and quantitatively accounted for. So we really have a very, very powerful tool at hand to predict diffusion coefficients. Not only in tungsten or nickel, but also in steel. And here are some examples of comparison of computed and experimental data for hydrogen diffusion in face-centered cubic steel, so austenitic steel. And it's almost embarrassing how well the blue line agrees with these the black dots here. Black dots are the experiment. The blue line is the computed result. And of course, if you go to BCC, so ferritic steels, in this case it's an iron chromium steel, diffusivity is much higher. So again, we do have a tool at hand to understand the diffusion of hydrogen, deuterium, tritium, and other elements in matrices. Now, in the context of maintaining and replacing the tungsten tiles from the first wall, we have engaged in a collaboration with the United Kingdom Atomic Energy Authority in England, near Oxford. And one of the questions was, well, if you have a hot tungsten tile that's loaded with tritium, and it's being manipulated and exposed to air, it will immediately oxidize. Will these oxide layers actually keep the tritium inside the tile, or will these oxide layers act as a window facilitating the release? And to this end, we have carried out systematic calculations of the energy, binding energy of tritium in bulk tungsten, in the interstitial sites, in vacancy sites as traps, in the WO2 oxide, and WO3. And you see a dramatic difference between the two oxides. WO2 is actually a barrier, very high diffusion barrier, very low solubility of hydrogen, but also deep trapping. In contrast, the trioxide, compared with bulk tungsten, is actually a getter, if you want, of hydrogen, with relatively low diffusion barriers. But of course, also if you have vacancies like oxygen vacancies, they can become very strong traps. So in other words, using simulations, we can get a very detailed understanding and quantitative data of the behavior of tritium in these oxides and the stability of oxides. Now, Another issue that Gerhard mentioned is if you expose these materials, for example, tungsten, to a neutron flux at a certain fluence, you transmuting tungsten into other elements. In particular, at first, you're transmuting tungsten into osmium and rhenium. First rhenium, later osmium. And after, in this case, a scenario of 5 years, you're ending up with rhenium and osmium in the material. Now, what happens to the properties of a material when you basically do the alchemy and change the material itself? Well, that can be answered by simulations using the so-called cluster expansion. And in this case, we looked at the behavior of tungsten when you transform and transmute part of the elements and the atoms into rhenium. Tungsten, the ground state, is a body-centered qubit. Rhenium is hexagonal close packed. So at which point does you tip over from a BCC lattice into the HCP lattice? Well, the good news is that that happens very late. So you need to have 0.7 atomic fraction of rhenium before the HCP phase becomes more stable. But there are other phases in between. So you could have either the cubic phase forming ordered or disordered alloys, or you can get the so-called sigma phase, which shows up in the phase diagram. So let's look at this sigma phase. Fascinatingly, the ordered sigma phase is thermodynamically less stable than disordered BCC phase. But if you introduce disorder into the sigma phase, then the configurational entropy stabilizes the sigma phase. And that's why the sigma phase shows up in the phase diagram. And so here's the sigma phase. In other words, again, using very accurate quantum mechanical calculations using VASP to combine with the cluster expansion, you can predict these kind of very subtle phase changes. Talking about the phase changes, a famous phase change of an oxide is in zirconium dioxide, which in the ground state at ambient temperatures and conditions is monoclinic. But as you heat it up, it transforms into a tetragonal phase and then ultimately into a cubic phase. Now, calculations have shown that oxygen vacancies in monoclinic zinc oxide stabilize the transformation to the tetragonal. So now we created, that was done by our colleague Volker Eyert, in collaboration actually with, again, the Naval Nuclear Laboratory, very nice machine learned potential for zirconium oxide. And if we now take two pieces of monoclinic zinc oxide, one fully stoichiometric, monoclinic, the other still monoclinic, but with 5% oxygen vacancies. And now we're heating it up. And so this is the dynamics that comes from these molecular dynamics simulations using our MLP. Oh, what you've seen is that the system with vacancies transforms sooner into the tetragonal phase than the stoichiometric phase. So again, these very subtle changes of phase stability caused by the presence of vacancies is properly captured with state-of-the-art machine-learned interatomic potentials that are trained on ab initio data. And it's probably fair to say that this capability of ab initio trained machine-learned potentials is kind of, well, I'm tempted to say phase change in how we are doing simulations of materials, but it's definitely a game changer. To take this further, let's go to the microstructure. In the case of oxidation of zirconium, you are forming over time when it's exposed to, for example, water or oxygen, you're forming an oxide layer that when you look closer, and this is a TEM image of such an oxidized zirconium system, you're forming a film of monoclinic zirconium dioxide, where the crystallites are in a columnar shape of about, almost 1 micron length, at maybe 100 or so nanometers in diameter. Now, using materials properties, namely the thermodynamics, the elastic coefficients, the diffusion coefficients, interface energies, the diffusion coefficients at interfaces, and there are many interfaces that you can have, which are being generated from first principles and machine learned potential dynamic simulations. When feeding that into a new module of MedeA called MedeA phase field, and to see what microstructure evolves. And in this simulation done by our colleague Kyle Starkey, lo and behold, you see the oxidation. So this is the zirconium metal. Here are the monoclinic zinc oxide. And if you put in the correct thermodynamics, the correct mechanics, the correct stress strain behavior, and interface energies and so forth, lo and behold, you're getting from the simulation quantitatively the same aspect ratio, the same pattern of columnar growth that you find in experiment. So in other words, what has happened here is that we've done true multiscale modeling, starting out with ab initio quantum mechanical methods, using machine learning to train potentials, use this potential to calculate all kinds of properties, then feed these properties, materials property data, into microstructure models, and we can predict microstructures. And now the stage is set to move all that information into, finite element structure analysis with well-known codes. And therefore, we've done true multiscale modeling. Now, this was just a snapshot of what we can do with the tools that are integrated in the MedeA. But the real purpose of MedeA is to empower you to do exactly these calculations with the best tools available and with the best support in this industry, because we have a team of very dedicated, highly qualified scientists who will work with you to make you successful using these methods. And all of that is integrated in a materials modeling environment that we call MedeA. It has databases, it has building tools, it has compute engines, for example, VASP, Gaussian, MOPAC, LAMMPS, GIPS, and the phase field code. Also the property predictors like Uncle for the cluster expansion. We then have workflow editors, so you can construct workflows, you can carry out high throughput, you analyze that, and the job server task server architecture is such that whenever you run a calculation, it's automatically archived, and of course you can reuse it later on, and you have a traceability of all your calculations with all the metadata. All that is integrated in MedeA, and so I think with that, you are in a position to carry out advanced state-of-the-art materials modeling of the challenges and meeting these challenges that we have as we are building these fusion machines. And just a final word about a new initiative that we are starting, namely Materials Design Fusion Alliance. So what is it? Well, we are bringing together the key players and the constituency of all the modelers interested in modeling these materials for fusion machines. And as part of the Fusion Alliance, you get immediate access to state-of-the-art multiscale materials modeling. You've seen a glimpse of that in the examples that I've discussed. We share the knowledge that we have and experience from these calculations. And the long-term technical and scientific software support is guaranteed because we are a company dedicated to long-term support of our customers. You have the ability to influence development in areas of critical need. You also, in this Fusion Alliance, have a forum for pre-competitive exchange of know-how in modeling of fusion-related materials. And you can use this software either on-premise or in the cloud, whatever your preference might be. And you have access, preferred access, to the contract research services that we provide at Materials Design. And for example, I mentioned this collaboration with the United Kingdom Atomic Energy Authority. That's done in the form of contract research, but it's really a very close scientific technological exchange. So I hope that this gave you a glimpse on what Materials Design is all about, what it can do for you in the area of modeling and simulation of the fusion materials. But before I end, I want to show the most important slide of our presentation, the acknowledgements, because it is always a team effort. And my first acknowledgement and thank go to all our thousands of customers of Materials Design. We wouldn't be there without them buying our software, buying our services, and providing input into our development directions. Of course, I want to emphasize the wonderful scientific and technological partnerships that we have, especially with Professor Georg Kresse at the University of Vienna and his entire team at the VASP GmbH, the VASP company. Professor Anta El-Azab at Purdue University has been essential in helping us getting into the field of phase field modeling. Professor Gus Hart at Brigham Young is a long-term collaborator in the field of cluster expansion. And then, of course, I want to thank all my colleagues at Materials Design, and especially Benoit Leblanc, who is our chief architect, Benoit Minicini, an expert in actually polymers, and also fluids, Clint Geller, who is coming from the nuclear field and knows a lot about this area and materials. Clive Freeman, our CEO, who has been a long-term colleague. We go together some 30 years or more. Dave Rigby, an expert in polymers. David Wright, who did the cluster expansion calculations. Garrett Toh, who did this beautiful collision cascade simulations. Jörg, working on machine learned potential. Kyle Stark and Leonid Kahle on microstructure modeling and phase field. Mariana Yaniraku, she's overseeing the overall release of MedeA. She herself is an outstanding chemical engineer. We've talked about fluids, but of course we can simulate lots of fluid properties. Michelle Kotjuga, she's an excellent support scientist. Mikael Christensen, well, I mentioned his name several times. He worked in the development of these MLPs and the zirconium oxide, and now the tungsten oxides. René Windix, leading our support team. Shubham, providing excellent and outstanding support. Volker Eyert, very much involved in machine learned potential. Walter Wolf, our expert in VASP and VASP interface, and Xavier, our resident quantum chemist and working on a number of properties and projects. So with that, hopefully I wasn't too long. I hand it back to you, Kathy.
Thank you. Hopefully you can hear me, Erich, at this point in time, and we'll get to a screen shared in just a moment here. I just wanted to open up the Q&A session. We have Erich and Gerhard back for a live Q&A session. If you would like to turn on your videos at this point in time. If you haven't had a chance to ask a question, please write your questions in the chat box for Erich and Gerhard, and they will readily answer these questions. They'll try to get to as many as time allots for us today. Just a couple of quick announcements. So while you type in your questions, you can do that on the right-hand side of the control panel up there in the corner. I did want to just, for your convenience, I have added a couple of slides that have webinars and modules related to this webinar. The first slide has a couple links to webinars on VASP and phase field that we've recently done. I have dropped the links here, so if you download these slides at the end of these sessions, you can easily link to view these webinars. You can also find these webinars on our webinars page, which has over 100 webinars of a wide range of content. I have added some related modules that may be use to you and links to their pages on our website. There are 5 of these modules that Erich and Gerhard recommended for me to share, and I have added them directly to this control panel as well, which you can download from the icon in the near the questions box at the top where you type in your questions right now. There's an icon so you can download those data sheets. We also have a MedeA high throughput training coming up Tuesday, April 29th from 8 a.m. to 12 p.m. Pacific. This session is tailored to introduce participants to the powerful capabilities of high throughput in MedeA software. And this online training is perfect for researchers, engineers, and anyone interested in mastering MedeA for advanced computational modeling. Welcomed are MedeA beginners as well as MedeA experienced users and those who have never used MedeA before. It's a 4-hour virtual session, including breaks and Q&A sessions. Attendees get to access MedeA, have access to MedeA, and each attendee can work through selected tutorials with the assistance of our fantastic support team, might I say. I also wanted to briefly call attention to our upcoming user group meeting in October. This will be in Vienna this year. Please visit our UGM page for more information. And we are running a little bit out over time, so I'm just going to stop there and not to do that so much in detail. But I would like to turn it over back to you, Erich and Gerhard, for the Q&A session.
Thank you, Kathy, and thank you to all of you who have submitted questions. So we realize we're a little over time, but I hope we'll have time to answer a few of them. How easy, Erich, you mentioned in a lot of cases, the use of machine learned potentials. Can you say a bit more about how easy it is to generate these potentials?
Before I answer the question, apologies. In the acknowledgement page, I forgot to mention someone obvious, namely Professor Krzysztof Pawlinski, who is the author of the phonon code. But our collaboration is so long that I just took it for granted, and so apologies to Krzysztof. Now, concerning the development of MLPs, machine learned potential, first of all, there is already quite a library of existing MLPs available in MedeA, so you can start with that. But we do have unique tools called the Machine Learning Potential Generator, MLPG, which allows you to generate potentials. And essentially what you have to do is pick a system that you are interested in, then define the configurational space that you're interested in. For example, you're interested in grain boundaries or in the diffusion processes. Then you create some smaller systems representative of the local environment. you perform in high throughput mode VASP calculations, collect all these data, and then you employ the MLPG that generates machine learned potential. Now, it is still somewhat tricky, I have to admit, but we are making life for you as easy as possible by providing automated tools. And if you really get stuck, well, then we just collaborate and create the potential together.
Can you please comment on nuclear waste management? So there's actually two waste aspects, at least two. The first one is, while in operation, the tokamak produces what you would call waste, for example, helium gases that need to ultimately be extracted in order to retain the right balance of deuterium and tritium, and that's what this diverter, which I mentioned briefly, is doing. The other aspect, nuclear waste, probably refers to the fact that absolutely when you have materials under neutron bombardment, take carbon, if you bombard a carbon with a neutron and the neutron actually hits the nucleus and combines with it, then you end up with carbon-13, which itself is stable, so not much of a problem. But if you hit it again with another neutron, you end up with carbon-14, which is radioactive. So the upshot of that is that even in nuclear fusion, radioactive waste does get created. It's usually relatively low-level radioactive waste. And as a design principle, when you consider metals and, for example, in alloys, it is something very much to be considered to make sure that the lifetime radioactive half-life of any potential radioactive isotopes that are getting created is not too long. And at the moment, mostly that those requirements are being satisfied. But there is, that's why I said there is, of course, still some problem with radioactive waste. It's significantly less, or much, much less than for fission reactions or reactors. The next question is for Erich. It's about whether MLFF for tungsten is trained and if that's available publicly, the tungsten potential that you mentioned in several of your slides.
Well, there are actually two parts. The MLFF is an integral part of VASP 6 in MedeA, and it's automatically available. So, for example, this case of hydrogen diffusion in this tungsten crack was a VASP MLFF calculation. Now, the potential for tungsten hydrogen, we are in the process of making this available. But if you contact us, we can work with you to make you to give you access to this potential. Just let us know.
Thank you. Moving on, what's the training or initial structure set for the cluster expansion model for the tungsten rhenium system?
The UNCLE module in MedeA generates its own training set as you start. So, for example, you start with a BCC structure and an HCP structure, and you said, well, you can populate now and replace the tungsten atoms with a rhenium atom, for example, and create different structures. And then the system automatically learns, and by creating structures, estimating the energy and picking the lowest energy to do DFT calculations and bootstrapping itself. So it's a self-contained automatic procedure in UNCLE.
Thank you. Let me move to a question more of a business nature. So if I join the Fusion Alliance, how much of the MedeA software do I get access to?
Well, you get access to all the relevant pieces that you need in order to simulate your system. So, for example, it will be the VASP, the MedeA environment, the VASP lamps, the VASP with the MLFF, MLPG, and diffusion modules, MT modules, interface, microstructure. So I think it will be a fairly comprehensive package to address the questions that you're interested in. And again, our friendly sales staff and very competent sales staff will be happy to work with you, exactly providing you what you need.
Thank you. Here's a very interesting question. May I ask if the on-the-fly training of machine-learned interatomic potentials is fully automated by the mentioned MedeA module, and if the training data set is training data set included simply bulk data or surface interfaces as well? So this refers to the MLFF calculations.
So again, the MLFF calculation with VASP, the generation of the training set is actually done automatically. You don't have to do anything else, but you get essentially potential just for that system that you're interested in and that dynamics. If you want, it's like a turbocharging of your ab initio molecular dynamics. On the other hand, if you're interested in generating a very generic MLP, machine learned potential, either, for example, as a form of a SNAP potential or an ACE potential, atomic cluster expansion, then what you do is you create training sets that resemble and capture the structures that you're interested in, for example, surfaces or interfaces or various phases, and you use MedeA VASP high throughput to generate these structures. And then there's a tool called MLPG, Machine Learning Potential Generator, that takes this training set, generates a potential, and typically you run several iterations. So you generate a potential, you try it out to see, but I'm not properly representing certain configurations. So you add them to the training set and refine the potential. So that's more of an process that you are involved more explicitly. So again, MLFF in VASP for specific systems as a turbocharger for specific molecular dynamic simulations on systems that you can handle with VASP, and MLPG training a potential that is generic and then can be used for very large systems like 100,000 atoms if you want. I hope that this answers the question.
Thank you. Here's a question: to what degree can your code be used to find novel candidate alloys or other materials with properties needed for a fusion reactor? I'll maybe answer the first part of that. Basically, if you look back at the slide I had with publications, or you simply do a Google Scholar search, there is actually a vast array of literature where VASP in particular has been used to characterize and also design materials, especially alloys. So the software can very much be used for finding novel candidate alloys. The software can also be used to parameterize other models like machine learned models, etc., by performing calculations on a fair range of alloys and then using machine learning and the like to vary this even more strongly to really get the desired design properties. So this is, I think, one of the strengths of the MedeA software, that it enables you both in itself to compute for specific alloys, properties of those alloys, and also to be used in conjunction with other codes to design those alloys for specifically the type of applications that we're talking about here.
Right. I mean, MedeA is a very open architecture. You have access to all the files and you can attach in custom stages your own programs if you want. So we don't want to hide anything, but at the same time, we want to make your life as easy as possible.
Here's one more. My question is, on the last study that you presented, where you mentioned that machine learned potential was used for the study interface, did you encounter any problems simulating the interface using machine learning potential in which long-range interactions are not included?
Not in this case. I mean, of course, it's a question when you have long-range interactions, for example, of electrostatic nature, then you need to pay attention to that. And one possibility is that in lamps, you can overlay different potentials. So you can use an MLP for basically short-range interactions and superimpose, if you want, an electrostatic field. But this is an active area of research, actually, to treat long-range interactions. Now, one approach that takes into account longer-range interactions is the so-called graph atomic cluster expansion, or GRACE. So we're working with Ralf Trautz in doing that. So far, what the system that you've seen, these long-range interactions don't play a role, and so they're well described. But it's a very interesting and important question.
Thank you. The next question I have here is, I'm about to purchase a license of MedeA. Should I rather join the Fusion Alliance?
Well, it depends. If your interest is in fusion-related materials, then I would definitely join the Fusion Alliance, and you get access to these tools and the tools that are specific to the fusion materials. But if you're interested in general modeling, you might as well just buy MedeA with the appropriate modules. For example, you may be also interested in polymers, which, for example, in the fusion world is not directly of interest. So both are good choices, and our very dedicated and capable sales force will be happy to explain and work with you to find the best solution for you.
Thank you. I think we have time for one or two more questions. So here's a question. Which processes of materials allow you to create columnar grains, zirconium oxide?
Well, that was the result of applying MedeA phase field. So this is the phase field module that is being used, and so it's an integral part of MedeA. It turns out that if you include the proper mechanical constraints through the provision of the mechanical elastic properties and interface properties and diffusion properties, this is the result, this is the output that you're getting. And you then can visualize the results as they're being produced.
Thank you. I'll ask one more question that I see here. What does one gain creating extra particles in nuclear fusion reactions? I'll take that briefly. Not entirely sure what the direction here is, but obviously different nuclear fusion reactions create different particles. One point that I perhaps skipped over a bit is, so if you leave aside the deuterium-tritium reaction, if you take fuels like deuterium helium-3 or proton-boron, then one of the main particles you gain there is an alpha particle coming out, basically a helium stripped of its electrons, very fast alpha particle. And I skipped over that part a bit. One of the advantages is that because it's charged, you can basically generate an electrical current, or this generates an electrical current, which can then be directly transformed, at least in theory, into electricity. And the efficiency of that process could be much, much higher than what you can achieve with a neutronic particle. So I'm not sure that fully answers the question, but that is one aspect that I wanted to highlight a little more. At fusion energy conditions, both pressure and temperatures can get extremely high. When modeling the surface of tungsten, the pressure may fall drastically. How do you model the tungsten surface at high pressure conditions?
Well, it may sound those are very high pressures, but actually simulations are particularly powerful under extreme conditions. So I think there's fundamentally no issue in simulating. Now, let's be clear, the plasma region is actually a vacuum region, and it's really the high temperature and the high velocity of the particles that impinge on the tungsten surface, which cause ablation on the surface. I mean, there has been already a number of studies of exactly this problem. Now, also, most of the energy comes from neutrons. And of course, when you look at the neutron hitting a tungsten surface, it has to hit a nucleus, which is very, very small. So actually, neutrons penetrate very deeply before they collide with tungsten atoms. So in other words, simulations are capable of describing these interactions, but of course it depends on the quality, how you simulate and describe the interactions, either with an interatomic potential or directly with ab initio. But fundamentally, it can be done.
Thank you. The next question relates specifically to slide 27. The question is a bit specific here. Is the MLFF training being done for 500 picoseconds, or is the production run actually being done for 500 picoseconds on slide 27? And do you do a temperature ramping for training from 300 Kelvin to 1000 Kelvin, or run equilibrium MD simulations?
Is it that one? Or was it more the traffic? In any event, let me explain the difference between ab initio molecular dynamics with VASP with MLFF. There, you actually train on the fly, and the purpose of these simulations is typically you have one particular system under particular conditions. For example, you're heating up a tungsten and you watch the diffusion of hydrogen atoms and as they're being trapped. And then as you're running the production run itself, you are generating a machine learned potential on the fly for that particular system and accelerating the dynamics. Now, in contrast, when we looked, for example, at the phase transformation of CrO2 from the monoclinic to the tetragonal, there we used interatomic potential, which was trained for a large variety of different zirconium oxygen systems, so maybe of the order of 5,000 different structures, and then you basically follow the protocols of a typical molecular dynamics simulation. You equilibrate and then you do a production run. So again, we have tools to run for a particular system with VASP, MLFF, accelerated ab initio molecular dynamics. And then we have tools, the machine learning potential generator, that is designed to create very general machine learned potentials for a wide variety of different configurations, and then you apply the typical molecular dynamics protocols in LAMPS. So I hope that explains the difference and the complementarity of these two approaches.
The next question is very closely related to that. Can you specify what type of machine learning potential did you use for the simulations? And you explained that in fact there's two types: the machine learning on the fly potential and MLPG generated potentials. How is the scalability of the force field is the question. What's your maximum simulation time and system size? I'll just
that's a very good question.
Yeah, go ahead.
In the case of the VASP MLFF, it's a kernel method somehow related to the Gaussian approximation potential, but implemented in a different way by the group of Georg Kresse. So it's this type of potential. In the case of the zirconium oxide and also the simulation of the trapping of hydrogen atoms in a vacancy of tungsten, that was a Q-snap potential. So the potential that and form that was developed at Sandia National Lab by Aidan Thompson and collaborators. And the scaling in terms of system size is linear. And you basically, there's no hard limit. We have simulated thousands, tens of thousands. We can simulate 100,000 of atoms. And we can also simulate long time scales. these potentials are quite stable, as opposed to some of the neural network potentials that when you run very long simulations can have instabilities. We didn't see that. These are very stable potentials, and they also include the so-called ZBL term for very short-range interactions, and that's useful for the cascade simulations. When atoms come very close, you essentially have screened Coulomb interactions, which are described by these CBL corrections. So yeah, I mean, the scaling, we can run many nanoseconds if you want to. You're limited by your compute resources.
Thank you. Next question is more of a technical nature about MedeA and how you can run it. So the question is, can you use MedeA on HPC clusters, GPU-based or VPU-based clusters?
The answer is yes, yes, yes. So MedeA is designed to can run on various different platforms, and we have many customers who run on HPCs. And MedeA has a three-tier architecture. You have the user interface. You have a job server that manages, for example, workflows that you specified in the interface. And then you have a layer which is called the task server, which do the heavy-duty numerical work, but they are lightweight so that they can be run on HPCs, on GPUs, and so forth. So yes, we are very flexible, and also typically when you have tricky installations on HPCs, because sometimes the queuing systems are very specific, we have an excellent and very competent support team that helps you to do this implementation.
And again, I'll just add also that once more again, the training that Kathy already mentioned on the 29th of April, that also deals with how you can use in particular high throughput calculations within MedeA. And so for those of you interested in learning more about how that works, that's an ideal training. Final question that before we want to close the session would be, is it possible to simulate the plasma material interaction with molecular dynamics? Usually empirical potentials are designed for neutral materials rather than plasma. So this is again really about, I think, partly about the materials.
Yes, I mean, in part the question has already the answer. It's a question of what kind of interatomic potential and are you using to describe that? Now, we need to ask the question, what problem are you trying to solve? Is it that you worry about destruction of the surface layer of tungsten? So, for example, you have high-speed helium nuclei impinging on the surface and damaging the surface, or is it something else? Are these electrons that are hitting the surface? So, depending on the question that you're trying to solve, you need to choose the correct potential. Now, that is, of course, one of the reasons we want to have this fusion alliance, where we develop, share, and assess these type of computational approaches.
I think we are kind of over time at this point. So thank you all for your questions. If you do have additional questions, please email Kathy or the team, and we'll endeavor to try and answer those after the webinar. And I think I'll hand back to Kathy at this point.
Thank you, Gerhard. I had a bit of trouble coming off of mute just now. As he said, this does cover most of the questions and comments that we have time for today. We've gone a little bit over. So if you have any more, please feel free to send an email to info@materialsdesign or khollingsworth@materialsdesign.com. That's me personally. I'd be happy to direct it to the right person here. If you have any questions about webinars in general or the upcoming training, I'd be happy to answer that, and any other logistics for the webinar. Let me conclude by thanking you, Gerhard and Erich, for your time today. And thank you all for joining us today for your questions and comments. We very much appreciate feedback on those surveys that will pop up in a moment so that we can tailor webinars that serve your interests. And we look forward to having you and your colleagues in a future webinar. Have a wonderful day.
Bye for now.
Bye-bye.
Bye.